So let f and g be functions then we define the following. So 1, the notation parenthesis f plus g close parenthesis x to be equal to f of x plus g of x. This is read as f plus g of x. We have another definition, parenthesis f minus g of x, and it means what we think, which would be f of x subtract g of x. Our next one is the juxtaposition of f and g. So if we write them next to each other, that's the same as the function f of x times the function g of x. And then lastly, for 4, if we have f divided by g of x, it means what we think. We take the function f and we are going to divide it by the function g. So this is an expansion of our function notation, which allows us to create a new function from old functions. So we can add two functions, we can subtract two functions, we can multiply two functions, and we can divide two functions. With division, there is one thing we have to be careful with. This definition only makes sense as long as g of x doesn't equal 0. So that is, we must exclude the zeros of g from the domain. Because we are not allowed to divide by 0. All right. So at first, I know this seems like it's something, it seems a lot more complicated than it really is. So the good news is we actually know how to do this already. We just don't know that. So all this really is some new notation for us to take a look at. So let's take a look at example number 1. So given that f of x is x plus 7, and g of x is x squared minus 3x, find f plus g of 4. Okay, so this wants us to find f plus g of 4, so f plus g of x. Well, by our definition above, f plus g of x is really just the same as f of x plus g of x. Well, if f of x is x plus 7 and g of x is x squared minus 3x, then this is going to be equal to x plus 7, because that's f of x, plus g of x, and g is x squared minus 3x. Well, now all we need to do is collect our like terms. So f plus g of x is going to be equal to x squared, x plus a negative 3x is negative 2x, and 7 doesn't have any like terms, so plus 7. So f plus g of x is x squared minus 2x plus 7. But it wants us to find f plus g of 4. Well, that means everywhere I see an x, I am just going to replace it with the number 4. So f plus g of 4 means exactly what we think it does. So it's going to be 4 squared minus 2 times 4 plus 7, which is 4 squared is 16. Negative 2 times 4 is negative 8 plus 7. So 16 minus 8 is 8. 8 plus 7 is 15. So f plus g of 4 is going to be 15. So other than the new symbols, this is exactly the same thing that we've done since introductory algebra. We're collecting like terms, and we're just replacing x with what it's the same as. So with function notation, it's really easy with function algebra to overthink the function notation. So it literally means what your intuition says, which is we're just going to add these things together and so forth. All right. So it's your turn. I'm going to break you up into your groups. Let's go ahead and do you try number 2. All right. So to do our you try, we need to do f minus g. So that's going to be f minus g of x is the same as f of x take away g of x. So that's going to be 2x minus 1 minus x cubed minus 5. So then we're going to distribute our minus sign into our parentheses. So that's going to give us 2x take away 1 minus x cubed plus 5. And then we collect our like terms, so we get negative x cubed plus 2x. And then negative 1 plus 5 is positive 4. So then our f minus g of x is negative x cubed plus 2x plus 4. So then finally, finding f minus g of 2, we replace our x with a 2. And that gives us negative 8 plus 4, which will give us 0. So, once again, just be careful with our signs, but we're going to be doing the algebra just like we've done in our previous classes. All right. So let's take a look at our next example. Before we do, we need to write a couple of things down. So the domain of the algebra functions is the and or intersection of the domains of f and g. So to find the domain of the algebra of functions, you would find the and or the intersection of the two domains. So similar to what we were doing in Chapter 1, Section 6. For f divided by g, we must also exclude the zeros of g from the domain. And hopefully that should be intuitive because we're not allowed to divide by 0. So if we have f divided by g, we would also, since we're dividing by g, have to exclude
G is not 0.
Yeah, so g can't be 0. Perfect. From the domain. All right, so now let's go ahead and take a look at our next example. In fact, I'm actually going to do you try number 2. So given that f of x is equal to x squared plus 1 and g of x is equal to x minus 5, we want to find f divided by g of 5 and the domain. So I'm going to add that to our problem. So f divided by g is going to be f of x divided by g of x. So in this case, our f of x is x squared plus 1, and our g of x is x minus 5. So if we try to replace x with 5, we get 5 minus 5, which equals 0. So it's not in the domain. And we'll note that x equals 5 is a 0 of g of x. That is, g of 5 is equal to 5 minus 5 is 0. So remember that a 0 by definition was an input that when we put it in, we get 0 as the corresponding output. So let's formally find our domain. So we need to find the domain of f, and we need to find the domain of g. Well, if we look at f, f has domain x squared, or f is x squared plus 1. So what would the domain of f be? Well, is there any number that you can't multiply by itself and add 1? And the answer is no, so the domain is all real numbers, so it's minus infinity to infinity. And what's the domain of g? Well, if we just look at g by itself, g is x minus 5. Is there any number that you can't subtract 5 from? And the answer is no. So its domain is also all real numbers. But the last thing that we need is we also need to exclude the zeros of g. So as we talked about before, the zeros of g of x are, or the 0 of g of x is, there's only one, x equals 5. So the domain is the and, so if we were to draw it on a number line, I make this one yellow, and I make this one blue. So if I shade everything, and then I shade everything, yellow and blue make green, so that's my and, but then I have to exclude the zeros of g. So if I exclude 5 from my domain, and this represents my and, it's going to be from negative infinity to 5 unioned with 5 to positive infinity. So that would be the domain of f divided by g. All right, let's keep illustrating this. I know it's going to seem backwards, but we're going to jump back to example number 2 now. But for example number 2, we're going to only find its domain. So we want to find the domain of f times g. So let's start with f. So how do we find the domain of a radical function? So remember, we take the radicand and we make it greater than or equal to 0. So we add 11, we add 11, and we get x has to be greater than or equal to 11. So this is the domain of f, and then we have the domain of g of x, and g is 3x plus 2. So since it's a linear function, they're going to have domain all real numbers. So from minus infinity to positive infinity. And I really shouldn't use purple. I should have used yellow. I want yellow and blue, which are going to make green once again. So I graph each of their domains, and the domain is the and. So here's the number 11. I want my x values that are greater than or equal to 11. And then my g is going to be everything, so I plot it this way. And then this is going to be my and is going to end up being 11 to positive infinity. So the domain of f times g of x would be from 11 to positive infinity. So once again, the domain for the algebra functions is going to be the and of the two functions, and then if we do division, we also have to exclude anywhere that would lead to division by 0. So example 3 is going to be the same thing, but it is done graphically to help us with this. So we need to answer our questions A through H. All right, so if we start looking at this, we want to answer our questions. We want to find the domain of f. Well, f is our graph in blue. So our smallest x and our largest x. So since our arrows point to the left and the right, our domain of f would be from negative infinity to positive infinity. Now we want our domain of g. Well, we find our smallest x and our largest x. So the domain of G is going to be from -6 to +9. Part C says find the zeros of f of x. And this is where remembering zeros, solutions, and x-intercepts are the same thing. So when it says find the zeros of f of x, it's also saying find the x-intercepts. So my x-intercepts occur where my graph crosses the x-axis. So the zeros of f are x equals -6 and x equals +6. Finally, my zeros of G are going to be where my red graph, or G, crosses the x-axis. So that's at x equals -4 and x equals +4. So now we want to find the domain of f minus G. Well, that means we need to find the overlap of these two domains. Well, the domain of f is everything. So if I shade everything, I get this. And the domain of G is the values between -6 and +9. So if I shade that part, I get that the and is where they overlap. So that's going to leave me with from -6 to +9. So now the next part says we need to graph f minus G. To help us do that, we're going to want to make a table of values. So normally when we make a table of values, we just do x, y. But we're going to add a couple of things. So I'm going to have x, I'm going to put my f in there, I'm going to put my g in there, and then what I'm looking for is f minus g, which I'm going to put over here. So when trying to find x values that we want to use, we can obviously use anything, but we know our domain is only the x values between -6 and +9. So those will be a couple of good places to start. So let's pick -6 and then 9 for our endpoints. And then we need to pick some points in the middle. So when trying to pick x values, we want to pick x values where one of the graphs change from increasing to decreasing, or at a local max or a local min. So we notice our graph changes here. We have a max in G, and we have a min in x. So let's go ahead and pick those x values as well. So I have x equals to 0, and then my min occurs when x equals to 2. So let's look at each of these graphs and fill in what we know. So our blue graph is f. So what is f of -6? Well, we go to our graph, that's right here. What's our corresponding y value for f of -6? Well, that's 0. Then we go to 0, and what is my corresponding y value for f? Well, that's -6. And then we go to 2, and we get our corresponding y value is -8. And then finally, out at 9, we go up to our graph, and we get our corresponding y value is going to be 6. And now we rinse and repeat, and we do the same thing for G. So G of -6 is -1. G of 0 is going to be 2. G of 2, right here, is going to be 1. And finally, G of 9 out here is going to be -2.5. But our goal was to find f minus G. So that's going to be 0 minus our g, which is -1. So 0 minus a -1 is 1. And then we have -6 minus 2, which is going to give us -8. And then we have f minus g, so -8 minus +1. So -8 minus 1 gives us -9. And we have 6 minus -2.5. And minus minus makes it positive, and we're going to end up with +8.5. So now this gives us a list of ordered pairs. So in green, -6 pairs with 1, 0 pairs with -8, 2 pairs with -9, and 9 pairs with 8.5. So we plot these points, -6 and 1. And then we plot 0 and -8. So we connect those. And then we plot 2 and -9. And then lastly, we plot 9 and 8.5. And we get something that looks like this. So that would be our graph of x, f minus g of x. So just as a recap, we found the domain, we picked those as endpoints, and then we found any maxes or mins, and we used those as inputs, and then we just actually calculated f minus g. And then we were able to plot all of those points on our graph. And that gave us our graph in green, which represents f minus g. All right. But instead of excluding the zeros of f for h, we need to exclude the zeros of g. Well, what were the zeros of g? The zeros of g were -4 and 4. So if we exclude those values, we have -4 and 4, and we exclude them, then we're going to end up with the following for our domain, which is from -6 to -4, unioned from -4 to 4, unioned from 4 to 9 included. So the things that we're excluding get the rounded parentheses as they're not included. Alright, so for the next example, we're going to be talking about the difference quotient. So to help us visualize the difference quotient, I'm going to draw a picture. So the idea of the difference quotient is, well, how do we find the slope of something that's not a line? And this idea is actually related to the average rate of change. So let's say we want to find the rate of change, or the slope of this graph at this point, x. Well, it requires 2 points to find the slope. So we have 1 point, we have x and f of x. To find another point, imagine we add a small positive number h to x. Well, that would move us to the right of the point x. to a new point, x plus h, f of x plus h. And now we could draw a line between those 2 points. Well, the idea is that the slope of this line approximates the slope of the red graph. So then that gives us our formula for the difference quotient. So the slope would be f of x plus h minus f of x all divided by x plus h minus x. So then, putting all of this together, we would get f of x plus h minus f of x. The x and the x reduce out, leaving us with just h. So this part right here is what we're going to refer to as the difference quotient. So that will be the formula that we're going to use for example number 4. So we're asked to find the difference quotient for the function f of x equals 1 over x plus h. So to use this formula, we need to have f of x plus h minus f of x all over h. So the first thing we need to do is figure out, well, what is f of x plus h? Well, f of x plus h says everywhere in my function where I see an x, I'm going to replace it with x plus h. So that gives me that f of x plus h is x plus h plus 1. So now my formula is f of x plus h minus f of x all over h. So f of x plus h, we just calculated, is 1 over x plus h plus 1 minus our f of x, which is our original function. So that's going to be 1 over x plus 1. And then the whole thing divided by h. And h is just from our formula. So now we need to simplify this. And the easiest way is to clear compound fractions is to multiply by the LCD. And our LCD in this case is x plus h plus 1 times x plus 1. So if we multiply the numerators of each of our fractions by our LCD, so x plus h plus 1 times x plus 1 minus 1 over x plus 1 times x plus h plus 1 times x plus 1, the whole thing divided by h times our LCD, x plus h plus 1 times x plus 1. When we do this, all of the compound fractions should reduce out. And that leaves us with x plus 1 minus x plus h plus 1 all divided by h times x plus h plus 1 times x plus 1. Distributing into our parentheses gives x plus 1 minus x minus h minus 1 all over h times x plus h plus 1 times x plus 1, and we reduce plus 1 minus 1 plus 8x negative x So finally, after all of that, we get -1 over, or negative h over h times x plus h plus 1 times x plus 1. And now our h's reduce out, leaving behind a 1 in the numerator, giving us our final solution is -1 over x plus h plus 1 times x plus 1. And that would be our difference quotient.